I'm here, Sasan.
You can start now. This is our final
Okay.
session.
All right. So who's the first speaker?
First speaker is Tatyana.
Okay. So can you I think you should just start. She is going to get started. Sorry, I was
Yeah,
late.
she is.
Okay, sorry, and yeah, please start.
Good afternoon. Thank you for the opportunity to present work my colleagues and mine. I'm a PhD student from Maltese State University, and today we'll talk about motion of submerged body is frozen channel with compressed porous ice. It's well known that ice is naturally non-homogeneous. Characteristics such as porosity, viscosity, thickness, and others can significantly influence its behavior. Moreover, tensile of compressive stresses may arise within the ice cover due to wind, current, or temperature change. These parameters must be accounted for the solving problems related to the ice cover. For instance, in the problem of a load moving on beneath or near the ice cover, the inhomogeneity of the ice affects the critical speeds of the load, the behavior of the ice, and its potential failure. The three-dimensional problem of interaction between an ice cover and the moving submerged body in a channel is considered. The channel has a rectangular cross-section with a width of 2b, depth of h, and its length is unlimited. The channel is filled with an ideal incompressible fluid, and its surface is covered with a thin ice cover. The submerged body is modeled by a three-dimensional dipole moving with a given speed. The problem is solved within the linear theory of hydroelasticity. In the linear formulation, the deflection of the ice cover W is modeled by the vertical displacement from the state of rest and satisfying the equation of the scheme viscoelastic plate. The ice cover is frozen to the channel walls, which is modeled by the clamped condition. The velocity potential of the fluid flow phi satisfies the Laplace equation in the channel domain, as well as the kinematic condition at the fluid plate interface. We considered porous plate. A model based on Darcy law is used to describe porous ice. The porosity is modeled by taking into account the velocity of liquid penetrating into plate on its lower surface. This speed is proportional to liquid pressure. Alpha is corresponding coefficients describing porous properties of the plate. At the walls and bottom of the channel, the flow potential satisfies the non-slip conditions. The pressure of the fluid and the ice fluid interface is given by a linearized Bernoulli integral. The potential phi represents the total potential of the fluid flow caused by both the motion of the dipole and the deflection of the plate and has the following form. Here, phi d is the potential of the fluid flow induced by the motion of the dipole, and phi e is the correction potential accounting for the fluid flow caused by the deflection on the plate. The submerged body is modeled by the three-dimensional dipole placed in the channel beneath the ice cover. The potential phi d is obtained using the method of mirror images to satisfy the corresponding boundary conditions. The correction potential phi e satisfies the Laplace equation in the fluid domain and the boundary conditions. The resulting system of equation describes unsteady oscillations of an inhomogeneous ice cover caused by the motion of submerged body modeled by a dipole. The ice in homogeneities includes variable thickness, non-uniform compressibility, and porosity. The questions of accounting for hydroelastic pressure is the porous model is important. For example, in the work by Mellon et al., the difference formula for the fluid penetration velocity in the ice was considered, taking into account only dynamic components. On the other hand, Zavьялова models, as presented in Zavьялова et al., included a term for hydroelastic pressure. The motion of submerged body along the frozen channel with constant speed is considered. Accounting for the velocity of the ice resulting in the attention of the ice deflection away from the moving body. Additionally, considering porosity also leads to the damping of these oscillations. These simultaneous considerations of these two parameters is not needed. For the considered problem, we will include only porosity for most of the calculations. At this stage of the solution, we shall consider a constant thickness of the ice cover and zero combined compressions of the ice. The problems are solved in dimensional variables. The body moves for a sufficiently long time with a constant speed, such that the ice deflection in the moving system of coordinates have reached a steady state form. In dimensional variables, the governing equation have this form. The sought-after function are the ice deflection W and the velocity potential, the fluid flow phi. The primary interest for analysis and investigation the behavior of the function W. The aim of the study is determine the effect of the dimensionless compression stresses Qx and Qy on the ice deflection and the distribution of strains in the ice cover. The problems are solved using Fourier transform along the x direction. Applying the Fourier transform to the plate equation and the boundary conditions, we arrive at this system. The solution of transformed plate equation is sought in the form of series of normal modes. The normal modes Pn are the solution to the corresponding spectral problem. The coefficients Am are to be found after determining Pn. The solution to find spectral problem is a combination of trigonometrics and hyperbolic function. The method of the solution to describe only for even modes. To find the Fourier transform of the correction velocity potential, first we introducing the function phi1 and phi2, such that both of these boundary problems are solved using the method of separation of variables. The resulting plate equation reduced to an infinity system of algebraic complex equation for the coefficients an. By multiplying this equation by the mode pm and then integrating the results of the y from -1 to 1. The resulting algebraic system is solved using reduction method, limiting the number of normal modes by n mod. The plate equation reduced to the following matrix problem. The solution to the matrix problem is solved by separating the real and imaginary parts of the vector as complex and reducing to matrix problems for the real and imaginary parts of the matrix equation. The deflection of the ice W are obtained using the inverse Fourier transform. We shall also study the distribution of strains in the ice column. They describe problem of the ice response with non-uniform compression caused by the moving submerged body is solved numerically for an ice plate with the following parameters specified on the slide. The values of the body speeds are chosen according to the critical speed of hydroelastic waves propagating in the frozen channel. The main varying parameters in the calculation are the dimensionless compression parameters Qx and Qy. The compressive coefficients Qx and Qy in the plate equation can change the value of phase speeds. Thus, the ratio of the body speed to the phase speeds and case of compressed ice will be different. In the case of compressed ice, the characteristics of periodic hydroelastic wave in a change were investigated by Batyayev et al. The phase and the group speeds for the first hydroelastic wave with the lowest frequency for the considered channel are shown in figure number 2. For the moving body, the phase speeds are most important. It can be observed from the plot that speeds equal 3 meters in second in subcritical for the uncompressible and weakly compressed plate. However, to high compression when dimensionless compressive stresses along the channel Qx equal 2.12 and Qx equal 2.477. The speed becomes supercritical, and there should be one long when the will propagate behind the body, and the one short wave that will propagate in front of it. Note that in the case of Qx equal to 0.477 for a low speed of the body, the long waves will have a negative group speed. Also, this value is a limit beyond which the characteristic of waves will be not physical. The effects of compressed ice along the x direction is shown in figure number 3. The calculation were carried of speed equals 3 meters in second. This speed for different value of compressibility Qx can be their subcritical, critical, or supercritical. The speed equal 3 meters in second is subcritical for Qx equals 0 and Qx equal 1. In this range, there is increase in the amplitude of ice deflection and strength in the local area above the moving body. Hydroelastic wave do not propagate from the moving body. Next, for Qx equal to 2.12 and Qx equal to 2.477, the speed is supercritical. Analysis of phase speeds predicts the appearance of one short wave in front of the body and one long wave behind it. These waves all are observed in the plot. The variation in compressive stress across the channel Qy does not lead not noticeable change in the phase speed of hydroelastic wave in the channel. Therefore, in the case of compressibility along the y direction, the shape of the ice deflection should not significantly change compared to uncompressible ice. The effect of compressibility across the channel is shown in figure number 4. For the subcritical speed equal 3 meters in second. The simultaneous effects of compressive stresses along and across the channel is shown in figure number 5. In the presence of non-zero longitudinal compressive stresses, The addition of transverse stresses amplifies the effects of longitudinal ones. Therefore, if a certain motion speed was subcritical even for longitudinally ice, it may become critical or supercritical with the presence of transverse stresses as well. Another notified special case is Qx equal to 0.477. In this case, the body speed equal 0 meter in second becomes critical. This means that the ice plate become unstable in the absence of motion. Dimensionless ice deflection and strength along the central line of the channel for x equal to 0.477 are shown in figure number 6. The ice deflection and strength increase as the speed of the motion approach 0. A more detailed investigation of these special speeds requires consideration on non-stationary and non-linear models. Accounting for the viscosity of ice as well as accounting for porosity lead to a decrease in ice deflection from a molten body. We compare the effects of ice viscosity within the Kelvin-Voigt model and porosity within the Malon model. To incorporate viscosity, we reformulate the problem by setting alpha equals 0 and tau non-equal 0. The solution method remains unchanged. Change will occur in the calculation of the edit mass matrix and the resulting matrix equation. For the comparison of viscosity and porosity effects of ice, the ice deflection and strains were calculated for a compressed ice cover along the x direction with Qx equal to 2.12. The dipole speed equal 3 meter in second. It is clear that increasing the porosity parameters dampens the waves both before and after the submerged body. Visually, increasing the porosity parameters slightly reduce the wavelength. The tendency of the permeability coefficients K to 0 leads the form of ice oscillation to a form of periodic waves, which will propagate into infinity. In the case of viscous ice, figure number 7 BND, the ice deflection and strains decrease significantly in the area of submerged body location and rapid dump it away from it with increasing tau. Additionally, it can be observed that with increasing viscosity, the wavelength slightly increases, which is opposite to the effect of porosity. Change in the thickness can significantly affect the behavior of ice cover. We consider the ice thickness variation function in the following form. The ice thickness is expressed in dimensional form and scaled by the value of H0. The value theta equal 1 correspond to the ice thickness of 2H0 near the channel walls for n equal 1 and 4H0 meters for n equal 2. To solve the problem, we also applied the method of normal modes for an elastic beam of constant thickness. The shape of the ice deflection quality remains the same. An increase in the variation in symmetric ice thickness leads to a slight increase in ice deflection amplitude. a variable ice thickness can lead to change in the parameters of hydroelastic waves. In the case under consideration, the linear ice thickness variation with small parameters, theta equal 0.25, does not lead to a significant change in the wavelength. Quadratic thickness variation with theta equal 0.5 leads to a 9% decrease in the wavelength. For large ice thickness variation, strains for less compressed ice may become greater than strains for highly compressed ice. The main results of the presentation are summarized on the slide. Thank you for your attention.
Thank you very much, Tatyana. And I know you started a little bit late as well, so you're keeping really well to time. Is there any questions?
Yes, I have a question.
Thank you, Yuri.
Yeah, Tatyana, could you show, please, your first slides? You mentioned that you took into account dissipation term in the plate, right? No. Next, slide 3, I think. On slide 3 here, right. So there is only one term which describes dissipation in the plate. Is it correct, my understanding?
Correct, is correct.
So there is only one term. How common this term for the description of dissipation in the plate?
Which is the term? Is it the tau term, Yuri? Is that right?
Yes, it is tau term, and I don't see any other dissipative terms. And my question is, how common this model?
Parameters is the viscosity and porosity.
I think Yuri's question is... I think the question, though, Tatyana, is this model looks new to us. We've never seen it before. So where did this come from?
No, actually, I did see such a model in other publications, but I'm not sure whether this is commonly accepted or there are any other models of dissipation.
Sorry, may I
yes,
say
please.
that here could be some problem for Tatyana to speak in English, to answer in English. If it's possible, I can translate question to her in Russian, and she will answer.
Great. Yeah,
great. Татьяна, вот у вас спросили вопрос первый, что у вас отвечает за затухание, вот, и про Тау спросили. Вот Тау, это вот вы откуда взяли? Это известная модель какая-то или нет? Откуда она взялась?
За затухание отвечают параметры пористости, именно альфа, а именно коэффициент проницаемости К, который в него входит, и также параметр вязкости, а также по-другому еще называется время релаксации, тау. Его значения берутся из экспериментальных данных.
Это понятно. А вот откуда взялась тау-модель?
Maybe, Tatyana, you can answer in English.
It would be hard. She said that in this model there are two ways to damping the oscillations. First, it's this tau in the plate equation, and also porosity parameter alpha. It is also gives kind of dissipation effects.
What is this parameter alpha? I can't see it in the equation.
Alpha is in the kinematic condition. It's the porosity model. It's the fluid speed penetrating into the plate on its lower surface, and this speed was taken from the Darcy law. So, and about this model, too, I can give comment that this model was widely used by Kozin and his group. and he even made some papers related to comparison between theoretical results and the experiments made in the experimental tank. And they managed to find this value of tau, which will give accurate results for load motion or for underbody motion.
Yeah. Who was the author
Maybe
you
a-
mentioned?
Who? Say again, please.
What was the
Who-
name of the person who did the experiments that came up with the tau? It was like
Земляк.
cosine.
Земляк.
Okay.
Maybe you
In-
could write that in the chat. Yuri,
Yeah,
I'll
and
just ask her.
yeah, I understand the name, but in which paper in which journal the publication was?
Maybe it's not him. Maybe it was in book by Cousin and his group, which was printed in Russia some years ago. I could search it and send you if I find it. The main problem was that they considered it very large range of values for this parameter to satisfy the experimental data. And like one value is not every time is accurate for different parameters of experiments.
I think we should move to the next talk. I did want to make a comment myself quickly. This is a really great piece of work. It's very impressive. But one of the but my comment is that the porosity was not treated correctly in that paper by Malin et al. I'm not a physicist. I'm a mathematician. The mathematics was correct, but the physics was wrong. And that was I'm pretty sure that's known to you guys. But I wanted to make that because it was pointed out to me by Sasha Korobkin. All right, but thank you very much, and that was for that talk. It's very interesting.